Welcome to Trustworthy Machine Learning, Lecture 6. Last time we looked into attacking large language models, and we started the second part of the lecture, explainability. We looked into the goals and definitions. This time we jump into more feature attribution story. We're going to look into evaluation methods as well as methods themselves for doing attribution to features. So what do we mean by attribution to test features? So we have a given model and we have a given test sample, and the usual task that you do is let's say if it's an image, then you take a look at the prediction, right? So it goes through the convolutional neural network, which gives you some score map. And then after aggregating the spatial kind of predictions, you get some kind of output. And that's usually answering the question, what is it in the image? And now, talking about test feature attribution, we are now asking the question, why do you think it is a cat? One possible format for that could be the foreground background binary mask, like this one here. So when we talk about feature attribution, the features can take different shapes, different formats. For visual inputs, we can think of single pixels or groups of pixels. And for groups of pixels, you can also think of image patch or superpixels, where superpixels mean like bottom-up grouping of pixels that are likely to belong to the same object. An instance mask, which is a precise delineation of the object, like a cat in this case. So we can choose to attribute to different granularities here. We can also choose to attribute to higher level features or cues, like subjective attributes like cute, or more factual ones like furry. It has yellow eyes, it has 2 ears, it's an animal and it's a pet. Yeah. So we can also try to kind of attribute the prediction of cat back to those kind of high level attributes as well. For language inputs, we can talk about attributing to tokens. Yeah. So which token is contributing greatly for the prediction of the sentiment of the sentence, the positivity, negativity classification of the sentence. Okay, so that's the features. And now we want to look into counterfactual questions we want to ask about these features. So let's say we are interested in the attribution of the prediction to this set of pixels, this patch on the input image. What kind of question can we ask, right? Probably the most important question that we want to ask is, how much does this set of pixels, or how much does this feature contribute to the prediction of the cat? And for answering this question, we can ask some sort of counterfactual questions. For example, we can replace those pixels with orange pixels like here, or maybe something like gray pixels. In general, we want to remove the features. Yeah, we want to indicate that the feature is missing to the model, right? So we want to measure the reaction of the model when you remove certain set of features and see how much change in the likelihood of the ground truth, for example, or likelihood of the prediction changes as you provide these alternative values for these pixels. So there can be many options, including even just copying and pasting some other pixels, some other picture, instead of the pixels there. Yeah. So you can also do these kind of counterfactual questions for the entire image instead of just a single like region in the image. So for example, we can ask questions like, what if there are noises added on top of the image? Is the model still going to predict the same class? What if the weather condition changes, which is kind of more relevant for self-driving cars, for example? Um, and some others ask about the reaction of the model when you change the texture of the image, whereas you keep the original shape. So let's say you have a cat image like this in the first place, and then now you keep the shape of the cat, but you replace the cat texture by the elephant texture, and see how the model reacts to it. And the model is generally texture biased, so now Indian elephant is still predicted for this kind of image. So this kind of counterfactual reasoning is a great tool for understanding what's going on inside a model. Okay, so we are interested in the contribution of each pixel or each feature. And the typical kind of question that follows this is what is the most important feature in the test input? So you're not just asking about a single feature in an input. You kind of divide a given input into multiple features present and try to rank these features according to importance or contribution to the final prediction. And then you may be interested in just understanding what is the most important ones or the top 10% most important ones and stuff like that. And so if we consider all these kind of auxiliary computations that we wish to do to answer these counterfactual questions or set of counterfactual questions per test sample, we understand that this is pretty expensive if you just want to do it in a brute force way. So let's say our set of features are sliding window, okay? And for each case, we are replacing the sliding window with some alternative values, okay? And depending on how many sliding windows there are per image and how many alternative values we consider, we'll have quadratically many or even like cubically many ways of formulating counterfactuals. And for each of these, you need to compute the forward pass of the model, and that tends to be quite expensive if you do it brute force way. Okay, so people look into ways to do it in a more approximate ways and speed things up. Okay, so that's the rough introduction to what feature attribution is trying to do. Now, let's try to kind of measure how well an explanation method is doing in terms of feature attribution. We put a number to it so we can actually compare different approaches to attribute to features and say, yeah, which approach is better than the others. Before that, we kind of I wish to give you some kind of understanding of what evaluation is eventually trying to do. Think of accuracy prediction. What accuracy is trying to do is you have real world scenarios where you do some kind of classification. Okay, and of course you're wondering, among 100 cases, how many of these are predicted correctly? Okay, and that leads to a natural definition of what accuracy should be computing. Well, that's an easy case, right? For classification, it's quite not super complicated how we should formulate the task. Yeah, the task is given a test sample, predict the correct class, right? And then the corresponding evaluation is also not super difficult. But when it comes to XAI, it's a little bit more complicated because we do not have a shared understanding of what should be the final goal. There are so many different types of real-world problems associated with explainability. In the one case, people may be wondering, yeah, my model is failing in certain cases, so I want to fix that. And for that, I need to understand what's going on inside the model. In the other cases, the use case is a little bit different. You have developed something, right? And it's working decently, but just presenting accuracy is not sufficient to persuade the customers that the system is reliable enough. So you need to come up with some additional metrics or additional tools to convince the customers further. And for that, you need better explanations beyond the accuracy metric, for example. So, yeah, there are so many different cases here, and there's no single kind of metric or single kind of protocol evaluation setup that's gonna fit all the needs here. And so, what people do is, yeah, there are many real world problems, but we focus on a subset of this and do some abstraction to find out what are the common elements. Yeah. And then as a result, you basically come up with some well-defined subtask, which is easily quantified. So for example, in feature attribution, we kind of look into the subtask of determining the change in model output when certain features are altered, the counterfactual questions. Because we believe that that element, this module, is kind of used in so many different downstream real-world problems. So instead of kind of visiting every single real-world problem in this domain, we just focus on a very important element, which is measuring the attribution of the features, attribution to the features. Or yeah, as I said, the other important question is the ranking aspect for all the features. So which feature is, for example, the most important feature for the prediction? And now there's, of course, third element, which is, yeah, if you just want to do two, then you can just do it, right? Because you can do as many forward passes through the network as you like, and you're going to get the answer to the question here. But usually this is super expensive, so you want to find a way to do it more efficiently. And so we can kind of take a look at those two transitions from the most reward-ish kind of settings to identifying a well-defined task, right? This is often taken as granted. So practitioners will, yeah. So researchers say we understand, of course, that practitioners will be interested in this problem in the feature attribution. So we basically work on that. And they don't usually go to users and the end users to find out whether that is really the case. Of course, there are also some work that do that, right? Which is great. But my message here is that we should be aware that we are kind of, there's some implicit steps that are often skipped in practice. So we need to kind of keep this in mind, and whenever necessary, we need to challenge this. And then the second transition from a well-defined task to approximation, this is actually the main focus of XAI research, I would say, in the AI domain. Okay, of course, in the HCI domain, human-computer interaction domain, a lot of people still look into the first transition from real-world problems to identification of well-defined tasks, which is great, and this is a burgeoning area of research as well. But if you kind of take a look at the current papers in AI, you're going to see a lot of papers just doing the approximation of the task. Okay. So here, what's important is the soundness evaluation for this transition from a task to approximation. So make sure that the approximation is actually computing the target task sufficiently well. Okay, so before talking about evaluation, let's wrap things up, right? So the definition of task is written as here. So measure the change of model outputs when certain features are erased. And the definition of erase here will be defined more clearly later on. So that's the task. And the computation of ground truth is trivial, right? You can just erase each feature and compute the corresponding model outputs. So you can just do it. It's just that it's super expensive. So you come up with some approximate algorithms for computing this, and then you measure the soundness, whether the approximation is correct, and efficiency. Okay. So that is actually covering quite some ground here among the 6 criteria for XAI evaluation: counterfactual, soundness, and efficiency. What about the other criteria, right? Selectivity. It's actually often possible to just measure the number of features selected when the explanation method is kind of pointing to the important features, right? Or we can even just control the number of features to attribute to, okay? And that's how we control the selectivity of the explanation. Social and interactive explanations. These are not often considered in the evaluation. We won't focus too much on that in this lecture, but I'm just mentioning that that's also a very important aspect of explanation. Just leave it like that. End-to-end usefulness, okay, which is kind of encompassing the full pipeline from real-world use cases to the task identification and approximation of the task. Yeah, so if you want to do end-to-end usefulness, then we have to kind of measure the performance of this full pipeline. We're going to introduce one method doing that, so with one evaluation method for doing this. So yeah, so in this case, we are questioning the validity of the task itself, right? We care about kind of ranking the features, but the question is whether that's really helping with the end-to-end usefulness of the evaluation of the explanations. Okay, we'll come back to that. So now we can come back to the question of soundness and efficiency. Even these two are causing enough confusion in the field. So I'm going to show you some of the previous approaches, earlier approaches in XAI, which did evaluation of feature attribution in a slightly wrong ways. Okay, so we have to learn how not to do it. So one example of that is qualitative evaluation. So given an image, we have a ground truth class, French horn, and on the right side, we are showing the corresponding explanations, feature attributions on every pixel. So red means higher attribution, blue means lower attribution. So we see that there are two methods here for feature attribution. One is gap. This is something called class activation map, which will be introduced in the next lecture. And then on the right side, we have backpropagation, input gradients, which we will introduce in this lecture. And they're trying to kind of compare these two approaches for explanation. And they say that their CAM approach significantly outperforms the backpropagation approach of 23, based on this figure. Yeah, so they're basically saying the middle column is doing better than the right column. So that's an example of qualitative evaluation. Maybe you agree with that. Maybe you already spot something a little bit imprecise. They also go a bit further and say and introduce the ground truth location of the objects. So the red box here indicates the ground truth location of the snowmobile. Okay. And what they try to argue, is that when they use this cam, which is the upper row, um, the attribution is actually pointing to the right location of the object. So yeah, so the snowmobile is actually predicted here, and for apron, you are basically pointing to the right region for apron, which is slightly better than backpropagation based approaches where you also see quite some attribution to the person's face, right, for the prediction of snowmobile. Oh, sorry. So red boxes are based on the attribution map. So I think they're taking something like top 70% threshold for drawing the bounding box for this score map. Um, and then comparing this bounding box against the ground truth, which are given by the green boxes here. And they say, yeah, CAM is doing better than backpropagation, as you see here, because CAM is pointing more frequently to the right location of the object. They even go on and say, yeah, and measure the number of times where the max point of the score map, of the feature map, is inside the ground truth location of the object, ground truth bounding box of the object. And say, yeah, there are CAM approaches, which are basically gap approaches here. These are doing better job than the input gradients you see on the bottom. But here, still the question is, does it really mean that um, better localization is actually implying better explanation of what the model is doing? Okay, so that's a big question, and I wish to kind of gradually answer this question. So I wish to argue that good explanation is not alignment with human intuition. And I'm trying to argue here that um, this kind of qualitative evaluation or localization-based evaluation is um, some sort of measurement of alignment with human intuition rather than explaining the model itself. Okay, so why is that? So I'm going to show you some pathological case here. So given an input image, the predicted class here is dog. And when you check the supporting pixels for the prediction of dog, you realize that um, the corresponding pixels are actually from the cat region rather than from the dog region. Okay, so that means the model, according to this explanation, the model is actually looking at the cat pixels to make prediction of the dog. So this is a typical case where the explanation is misaligned with human intuition. Okay, so when this kind of thing happens, there are actually two possibilities. One is the problem with the explanation method. The model was actually doing a perfect job, right? The model was actually looking at the dot pixels to make the prediction, but for some reason the explanation is kind of pointing to the cat region for whatever reason, right? And then we are kind of saying that, yeah, the explanation is failing here. But there's another possibility, which is that explanation method is perfectly fine, right? It's just showing what the model is doing. It's just that the model is completely unaligned with humans, which is, of course, possible, right? Because we know from many of the previous lectures that machine models do not always align with humans' way of recognition, right? So, I mean, the main reason why we wanted to do explainability is because we know that the models are not working the same way as humans, and so there should be some kind of a communication channel or some medium for humans to communicate with machines, right? For machines to express itself to humans in an efficient way. So that's why we are looking into this in the first place. So let's conceptualize this a bit, okay? So what's wrong here, right? So given a model, um, you pass an input through the model, and you're going to get some output, cat, okay? And now, instead of just cat, you're also interested in the explanation, S, okay? And we note that the explanation here should be a function of the model itself and the input. So it's S of f and x. Here, the soundness question is asking, does S of f and x represent the true causes for f to predict f of x? And now, I'm arguing that the true explanation of why the model predicts S as y is a function of all of x, y, and f. Okay, so it has to be a function of the model as well. But if you do qualitative evaluation, the problem is that humans do not have an understanding of where the model is looking at. Okay, how the model is making the prediction. If we knew that in the first place, then we didn't need the explanation at all. So, in a sense, qualitative evaluation is only taking into account the input and the output, which are kind of human interpretable. And we are not kind of considering model F in the evaluation. So we should not do qualitative evaluation when we are doing explanation evaluation. Again, explanation with ground truth localization, which is slightly better than qualitative evaluation in the sense that you get some numbers and you do not rely on a very few cases. But still here, when we do localization evaluation for explanation evaluation, we are kind of implicitly assuming that the model should be aligned with humans in the sense that the model should be always looking at the true location in the image to make the prediction. But this is not the case, and one of the possible reasons why we want to look at explanation is precisely because this alignment is not in place. So we want to kind of analyze that. And this again is an evaluation that does not depend on f and only depends on x and y. So we should not do it. And now the question is, what is the right way to do it? And I'm suggesting to use remove and predict paradigm. Remove and predict evaluation means you're given an explanation, score map, S of f and x. Let's say this is for each pixel, okay? But it doesn't have to be pixels. It can also be a set of features which are not spatially organized. But in any case, the necessary condition for this explanation to be sound is that if it's sound, and then if you remove the most important feature as guided by this explanation map, score map, for example, the red pixel here, if you remove that feature, then we should see the greatest drop in the correctness of the prediction. In other words, we can measure the likelihood of the ground truth class of this image given the model after removing the most important pixel according to the score map. And we can basically measure that against the erasure of any other points. And our aim is to show that by erasing this most important pixel, we see the greatest drop in the likelihood of the true class. You can also gradually introduce the erasure, removal of the pixels. So when there's a score map like this, you can also remove gradually from the most important pixels in the image all the way up to removal of every pixel in the image. So if we write p% for that, we can go from 0%, 10%, 30%, all the way up to 90% and 100%. Here, the remove is defined by replacing the pixel values with gray, which is arguably removing the color information for that pixel. Okay, and for each case, we measure the model's performance. Yeah, how well the model is predicting the ground truth class. We wish to see a quick drop as we erase the pixels according to the importance as guided by the score map. To quantify this, we can measure the accuracies as you erase more and more pixels. So we can plot something like this, where x-axis is the number of pixels or the proportion of pixels we erase, k%. And on the y-axis, we have something called relative accuracy, which is the accuracy of the model for the whole validation or evaluation set, where you're erasing certain number of pixels per image, the same proportion of pixels per image, according to different score maps. In one case, you can use the score map as given by the explanation feature attribution method. Like, for example, COM and so this red and blue, these are giving pretty good results for COP dataset. Again, RK is kind of the relative removal. So given a method for the score map, you're always comparing against the random score map, which is ranking the features in a random fashion. Uniform random fashion. So because of course, if you're randomly erasing every pixel in the image or every feature in the image, you're also kind of removing information from the image. What's important is that as you erase information according to the score map, we should see much quicker drop in the information content. So we normalize the amount of decrease in the information content by always comparing against the random erasure. And so you have this random erasing baseline, which is now indicated as a horizontal line at 1.0 all the way through, because the nominator and denominator are kind of equal to each other. And compared to that, we are measuring how well each feature attribution is dropping the likelihood of true classes. Yeah, so for example, for this method here, the drop is quite steep, meaning that you are erasing quite some information pretty well. So the baseline, metric, we measure the drop, okay? And the quicker the drop is, the better, especially for the first part where we are focusing on the most important pixels. In the later parts, it becomes a little bit noisy as well, because now even for the random erasing, you're removing quite a bit of information from the image. So you don't have very reliable baseline accuracy for these cases. And the baseline accuracy could be very low anyways. So in those cases, maybe the random erasing is already pretty bad, and compared to that, maybe your score map is giving slightly better results and so on, but these are quite noisy estimates. So the signal to noise ratio here is pretty bad. That potentially explains why it may be possible to overshoot beyond the random erasure baseline. Okay, so here I want to kind of touch upon a very important issue with erasing pixels or erasing features in general. What people normally use for erasing information, erasing feature, is by replacing the pixel values with black pixels or gray pixels. Yeah, so what I'm trying to say here is that actually replacing the pixel values with black does not always reduce information. It's not always an indication of no information. Introducing those black pixels may actually introduce further information into the image. Let's say the original image looks like this, with an image of a flatworm, and then you're introducing some black pixels to erase information from some pixels. But now, when you pass this image through a ResNet 50 model, the model starts to predict something completely unrelated to flatworm, such as crossword, where the likelihood of crossword for the original image was arguably close to zero. But we kind of understand why this is the case, right? Because we see these kind of grid patterns of black pixels, and that exactly looks like crossword. So in this case, by erasing some of the pixels with black pixels, we're actually introducing new information into the image. And if you do it randomly, we get something like this. If we erase the least salient according to the score map, then we are kind of leaving only the central part. And that also kind of indicates uh, high likelihood for a jigsaw puzzle, for example. Or if you have this black blob in the middle, the model starts to think this image is of a cliff dwelling, which is one of the ImageNet 1000 class, 1000 classes. So by removing pixels, you're potentially introducing further information, which is not what we intended. So then we are asking ourselves this question of what would then be the best way to remove information? Again, you have this kind of image of all, yeah, so the correct prediction is made. So I use this online classifier for that. Um, and I'm wondering about the contribution of these set of pixels here, yeah, indicated with black pixels. So I removed those pixels and replaced the values with zero and passed through the model again. And what I'm seeing is prediction of not just all, but also home decor, even person with very high likelihood, 90%, and cushion as well, which are kind of clearly wrong. Okay, so by removing pixels and introducing black pixels, we are not just erasing information, but also introducing some novel information. So here, what we can also try to do is inpainting. Inpainting means for the designated region in the image, like the black pixels here, we wish to replace the values in a most smooth way and most natural way that you'd not think there was something. Yeah. So um, based on the contextual regions, you try to guess the most natural way to fill in those pixels. That's what inpainting means. Some people also call this imputation. And now, if you do inpainting using this online tool, you have something that looks a little bit more plausible than before. And because the generation of these pixels are kind of based upon the contextual features, which are kind of containing information that you're allowed to use for making the prediction, arguably you're removing information for the black pixels. But still, you're not introducing any artifacts which will make the model think there's some extra information apart from the because of these unnatural black pixels as before. Okay, so now, so we check whether we only decrease the information and do not increase any other information in the image. But still, actually, we find that baby class and person classes are still predicted with rather high confidence, 92%. So Inpainting is potentially a better solution, but still it also introduces artifacts which makes the model predict some random other class with high confidence. And the other caveat is that Inpainting can be quite expensive. But even with all these caveats, the reason why people looked into Inpainting in the first place is because it gives kind of a nice probabilistic formulation on why this is probably the most correct way of doing erasure of information. So from a probabilistic perspective, we can write down the likelihood of the ground truth class C given an image X as follows. So the quantity of interest for now is what happens. Yeah, what happens to the model's likelihood of the ground truth class given an image without certain region, which we indicate by X minus I, like this. And if you have X minus I and XI refers to the region that are erased. Then we have the original image if we have X minus I and XI together. Okay, so again, our quantity of interest is P of C given X minus I. And we can write down this value here as a decomposition of according to the conditioning on Xi. Okay, so Xi is some missing information that we don't have observation over, but we can introduce different possibilities for Xi given X minus I. Okay, so we can introduce P of Xi given X minus I, and we can condition the prediction of P of C also on P of Xi as well. So now we have this sum product rule, so we can sum over different possible values for Xi, and we do product of P of C given X minus I and Xi, and times P of Xi given X minus I. And now this can be written as with some Monte Carlo estimation. So you can do integration over different samples from the distribution of P of Xi given X minus I. But instead of P, we are introducing this approximation of the ground truth P using Q, a parametric model. So this model is kind of giving you proposals for Xi given X minus I. Okay, so we sum over these samples, and on the right side we have P of C given X minus I and Xi. And again, if you're conditioning on Xi and X minus I together, it's essentially just doing the prediction over the entire image given some proposed Xi values according to Q. And we realize that Q is exactly an instance of Inpainting model. Yeah, given contextual region, try to predict the values for the black region. Okay. Okay, so that's how it looks like, and so in other words, you produce multiple possible Inpainting of the black region, and then for each case, you predict the ground truth class. Sorry, the likelihood of the ground truth class, and you do the averaging of these predictions, and that's going to give you some sort of theoretically true prediction when you erase information for sure. But again, the question is whether Q is really nicely approximating the true distribution of P of Xi given X minus I, and that depends a lot on the parameterization and the performance of the Inpainting. But anyways, assuming everything is possible here, after computing P of C given X minus I, you can do the difference between P of C given X minus I and P of C given X. That's going to give you some kind of counterfactual difference that are introduced by erasing certain pixels in the image. If you like, you can also take a look at the logout, like here. Yeah, so that kind of explains again how to measure a contribution by measuring the model's likelihood when certain features are not available. Of course, in practice, my recommendation would still be to use black pixels or gray pixels, depending on the mean subtraction that you're using. Right. So yeah, so wrapping up this session, I'm proposing to use remove and predict, as opposed to qualitative evaluation or localization-based ones. Okay, let's touch briefly upon end-to-end evaluation next. So the list is huge. How, in which kind of scenarios can we use explainability? In one case, we are using that for model debugging, right? Identification of spurious correlations and ways to fix them. Improving generalization to OOD data. Yeah, or some people think the main goal of XAI should be kind of aiding human understanding. So do we then understand the idiosyncrasies of model better by looking at the model predictions or model attributions, feature attributions? Okay, so this is a boring list of possibilities. So let me give you more possibilities here. So given an input, again, we're trying to pass that through a model, and we get some likelihood for the true class, and we generate some explanation for that. So S of f given x. Let's say we have three different possibilities here for downstream applications. So in one case, we have debugging goal. So machine learning engineer is wondering how to fix the model, right, based on the explanation. On the other hand, scientists may be interested in understanding in the model. So you have some kind of data-driven system for understanding the physical laws, for example. So eventually you come up with some kind of dynamical systems based on the machine learning system. And now you want to understand what kind of rules, natural rules, has the model found. And the scientist is kind of expecting those found rules to be useful for expanding human knowledge. Instead of just making blindly predictions for future cases, they want to understand the mechanism. For doctors, maybe the end goal is really trust, right? In so many cases, machine learning models are doing so much better than human counterparts, and they offer very quick and efficient ways of processing data. The main reason, in many cases where humans do not rely on such systems, even if they are working better than humans, is because they lack trust. Okay, so the wish is that after providing this explanation, we have a greater signal of trust from the end users. So that could also be kind of the end goal of this as well. Okay, so far we have been focusing on the soundness of explanation, which is kind of the first part of this. But now, when we have more end goal in mind, we may also take a look at the whole pipeline that goes from the model all the way up to the downstream user. The caveat is that the end goal is often tied to human subjects. So to run this kind of evaluation, you always need to have some human in the loop. And so this may pose a lot of problems, like it's not reproducible, because depending on who you're asking, you may get different answers. Yeah, but let's still take a look at one possibility of human-in-the-loop evaluation for feature attribution. So let's say we have two kind of cases, Olf versus Husky and Leaves. So for Olf versus Husky, we wish to discover bias. The model's task is to predict whether a given image is containing a wolf or a husky. Usually, when you train a model for this kind of binary prediction task, the model likes to make use of background pixels. Yeah, because you see all in usual kind of background, like more. There's basically more correlation between the background and foreground in this case. So the hope is that by showing the feature attribution, we kind of understand better what are the features that the model is looking at and determine whether that's a good kind of valid feature or not. For leaves, we have more scientists in the loop. So, this kind of leaf prediction is pretty hard, right? We don't know what this means. But by understanding where the model is looking at to make these predictions, we gain more scientific understanding of which part of the leaf is contributing to each of these classes. So we wish to kind of measure the enhancement of human knowledge as a result of taking a look at the of the explanation, feature attribution. So here's the setup. We have human in the loop meta predictor, psi, and we are training a human to predict the model behavior in a sense. So we are presenting the original image and the score map for the feature attribution and the prediction of the model. We give k such samples, tuples, and kind of train the human to kind of understand the inner workings of this function f. And then what we are tasking the humans afterwards is we give a new image and we ask them, what do you think is would be the prediction of the model for this image, and check if the predicted prediction of the model is exactly the prediction of the model. Yeah, so in a sense, we are kind of training humans to kind of mimic the behavior of the model in the new cases. Right. So what is a baseline here, right? So maybe humans are already able to kind of, maybe the machine model is already aligned pretty well with human intuition. And so even without any training of humans, without those case samples to train humans, humans are actually able to understand what the model is going to do for this image. And that's exactly this psi 0 case. And our evaluation metric is a division of the correctness, the accuracy of human prediction of the model prediction, divided by the human prediction of the model prediction without seeing any of the samples. Okay, so when utility k is greater than 1, like statistically significantly, then that kind of means that humans do learn something out of this procedure. And here's the result for wolf versus husky, for example. By looking at a bunch of these kind of samples, given by different score maps, yeah, from GradCam, integrated gradient, and so on, you're able to go beyond 1.0 baseline in many cases. So the x-axis is the number of samples given to the human. So of course, when humans take a look at more samples, they seem to gain better and better understanding of how the model is making the prediction. And so we have an increasing trend in general. And yeah, in many cases, the values are above 1.0 again. We have this control setting, which is the red dashed plot here, which is given by showing some score map, something called bottom-up saliency, which do not depend on the model. So we see that if they take a look at some kind of fake medicine here, right? So they just take a look at some random score map. That doesn't actually help with predicting the model prediction. Almost the same conclusion is true for scientist in the loop evaluation as well, for leaves. So we also see that for most of the explanation methods, we see that presenting more of these samples introduce more useful information than just showing not showing anything, or the control group where you show some random score map. Okay, the dashed line here, which is great. So we can train humans to predict the model prediction. And now here we wonder about the relationship between the end-to-end usefulness of the whole task of kind of making humans understand the inner mechanisms of the model better in such a way that humans can now predict what the model is going to predict on the new sample. How is that actually related to remove and predict paradigm? Okay, so we have on the x-axis the remove and predict score. On the y-axis, we see the utility k-score as seen in the previous slide. The aim here is to measure whether there's a positive correlation between utility and faithfulness. And if there's a way to kind of replace the utility evaluation by faithfulness evaluation, which do not require any human in the loop. And so it's more reproducible and cheaper. Unfortunately, there seems to be no positive correlation in general. So, for example, we have even negative correlation across different methods for Husky variants here. For leaves here, we do not have any noticeable correlation. Actually, for the third task, which we did not talk about in this lecture, there seems to be a slightly more positive correlation, but still it's not super strong either. So here the main conclusion is that we do soundness evaluation a lot, but that does not guarantee end-to-end usefulness, and we always have to question whether the kind of things that we do in feature attribution are useful in practice. So we talked about evaluations, and let's move into methods. How to do feature attribution. Let's first take a look at continuous inputs. Again, brute force is super expensive. Sliding window patches, yeah. So how to do that more efficiently? Let's take a look at a very special case where the features are each of the pixels, individual pixels, and the perturbation is super small. Okay, so let's say the original pixel value for this is like this, almost a white pixel. And let's say we wish to make a counterfactual change for that pixel by adding a single number, 1 out of 255 for the red channel. Okay, and then let's say we observe a small change in the model output, 96.5%. That's kind of crazy, right? So we make something, some change which is not even visible to human eyes, and we are measuring how the model is reacting to that. How is that useful at all? I don't think that's useful at all to begin with, but conceptually, this is probably the simplest case. So let's start with this. Again, a dumb way of kind of looking at these counterfactuals is by computing forward paths several times for each perturbation of the image. You may have different forward passes for each perturbation of the pixels. It's actually going to be a number of pixels times 3 times because you have 3 RGB channels here. But we realize that doing this computation is actually equivalent to computing gradient. So you can do this computation efficiently by taking an input gradient and doing using backpropagation. You know, the definition of gradient for an input x, for the function f, is given by f prime of x, which is the limit of the difference divided by the difference in the difference in output divided by the difference in input, and the input difference is going down to 0. Okay, and that's exactly kind of the situation here, right? Because we have very small difference in the input, just 1 out of 255, and we have corresponding change in the output. So we divide those changes, and we are basically linearizing the instantaneous kind of change, the tangent line for this function. So conceptually, we have a multivariate input, right, for every pixel. So we are asking this question: what happens if you just add a delta value for pixel I? Okay, and then we're going to have the corresponding model output f of x plus delta ei, where ei is a one-hot vector corresponding to pixel I. The difference between these two values is given by the dot product between delta ei and df dx. Df dx is basically a vector, yeah? And this is again given by delta times the partial derivative of f against xi. And this is kind of giving some linearization of the function f as a function of delta, or as a function of delta and ei together, where you're going and how much you're going. Okay, but in practice, when you get the input gradient, you're actually going to have 3 channels, RGB channels, but in many cases, what you're wondering is the pixel-wise contribution rather than pixel and channel-wise contribution. So what people have done some time ago is to take the max across the channels. Okay, and also we are not super interested in the direction of change, whether changing the pixel to the bright side will change the model prediction positively or negatively, but we are rather interested in the size of the change of the model output. Yeah, so we take the absolute value to kind of remove the meaning of the sign of the gradient. Okay, and then take the max across the channels. Right, so that's the raw kind of score map. And now for visualization, you need to kind of put the range of values between 0 and 1. Okay, that's how you visualize an input, visualize a score map. So what you do is you normalize the whole score map by the max value of the score map. So these are kind of practical post-processing to make things feasible. Okay, so now input gradients come with many issues. Um, I already mentioned one issue, which is that the kind of counterfactual they are looking into is meaningless, right? Those infinitesimal changes in the input and infinitesimal changes in the output. What does that really mean, right, in practice? Um, the other problem with input gradient is that if you visualize it, it's super, super noisy. Yeah. So the kind of important pixels, according to the input gradient, is kind of spread across all region in the image. So here the question people asked was how to get smoother maps here. And the way they did that, they computed a smoother map is by using a method called smoothgrad, which is nothing but kind of averaging across um, multiple input gradients, where each of the input gradients is actually computed at slightly perturbed image, where the perturbation can be done by using some additive Gaussian noise, right? Epsilon here, with very small sigma value here for the variance. Yeah, and you compute the input gradient at different location of the input, different perturbation of the input. And then you take the average. And then you get something that's slightly more smooth than just vanilla input gradient. So conceptually, what we're doing is something like this. So given x, originally we were just interested in x plus delta EI. What happens if you change the input towards the for delta amount towards the direction EI. But we are not just doing that for input x in this case, but we are first perturbing the input x according to a Gaussian noise. So we're going to have x plus z1, x plus z2, and so on. And for each of these cases, we are kind of replacing the input. We are perturbing the input to the EI direction for the amount delta in every case. And then for each of the cases, we can kind of take a look at the difference between these two model outputs. So for example, for Z3, we're going to compare f of x plus Z3 plus delta EI minus f of zx plus Z3. Okay, so conceptually, and those differences are kind of averaged over different perturbations. So conceptually, we can write expectation over the perturbation z, and we take a look at the difference between f of x plus z plus delta EI minus f of x plus z. And this can be approximated by the gradient times the small factor delta, right? Okay, so EI times gradient of f with respect to x at x plus z. Okay, and we can do the swap between inner product and expectation because both are linear. And so finally we have delta times EI inner product, the expectation of the gradient. Okay, and that's why we are kind of taking a look at the average of the gradients at different locations. And that's what smoothgrad is telling you. Ez of the gradient of x with respect to x, and x equals to x plus z. That's what smoothgrad is. Now the question is, yeah, that's such a great tool, right? Can you actually do the same thing for a greater region in the input space? So far, we have been kind of focusing more on the local vicinity of x, but is there a way to kind of extend this to other regions in the input space? So one example that we have is integrated gradient, something called integrated gradient. And I'm going to tell you what we're doing here. It's not super different from smoothgrad. It's just that in smoothgrad, you're introducing different versions of the input by adding additive Gaussian noise. In this case, we are doing the random kind of search between two input points. So in this case, we have another input x prime, okay, and this is x. There's x missing here, and we do linear interpolation between the two in the input space. So that corresponds to x plus alpha times x prime minus x, where alpha could be between 0 and 1. And for kind of random uniform point along this line, you are asking this question, okay, what if you change the input to the direction EI, delta amount? How is the model reaction going to change? Okay. And then if we write this down, we have expectation over alpha, where alpha is sampled from uniform distribution between 0 and 1. The difference between f of x plus alpha x prime minus x plus delta EI minus the original value, f of x plus alpha x prime minus x. And again, we are approximating this by using input gradients evaluated at x plus alpha x prime minus x, the location of interest, right, at alpha. And we realized again that expectation over alpha could be inserted into the inner product itself due to linearity. And then we have something like integration over 0 and 1, and you are taking the gradient of f with respect to x at each location along the line. Okay, so we have a form of integration over the gradient, and that's why it's called integrated gradient. So in practice, we don't actually stop. So I'm just taking this evaluation, the equation here, to this slide here. So you're just taking the inner product between EI, the one-hot vector with 1 at pixel I, and the summation over alpha values along the line between x and x prime. And for each location, you're basically taking the gradient of f, input gradient. So why do we care about this quantity, right? Actually, if you take a look at input integrated gradient, there is actually one additional factor, which is xi prime minus x. So I'm going to explain why this novel factor has to be introduced. Okay, so let's assume for a second that we have this formulation, xi prime minus xi times the inner product between EI and the integration over alpha for the gradient of f against the input at different locations in the interpolation. Okay, so that's the contribution of pixel I for the final prediction, let's say. What kind of nice property does this formulation have? That's the question here. So to answer this question, let's probably try out summing these contributions for each pixel over all the pixels in the image. So we're going to do summation over I in front. And this summation over I time sum over I and xi prime minus xi, these factors can actually be inserted at EI here inside the inner product. And summation over I and EI times xi prime minus x is essentially equal to x prime minus x vector. Yeah, because you're assigning the vector values at each location I using the one-hot vector EI. Okay, so eventually we have integration over the inner product between the gradient and some vector. Why is that important, right? So for understanding the importance of this equation, we first need to kind of recall the fundamental theorem of integral, or its generalization to line integrals in higher dimensional space. Fundamental theorem of line integral says that if you're integrating over the parameter t at a up to b, and if you're kind of taking the inner product between the gradient field of phi along the line and the speed and the velocity along the line, then eventually what you get is the difference between the potentials, the phi of r of b minus phi of r of a. Yeah, so taking that as granted, we can just plug in different formula here, phi and r of alpha, okay? So if we plug in phi, f to phi, and plug in r of alpha according to the interpolation here, then we derive the following property. The integration over 0 to 1 for alpha over the integral, the inner product between the gradient, input gradient, and x prime minus x, it's actually exactly the form of the above fundamental theorem of calculus. And it basically tells me that the result of doing this integration is exactly f of x prime minus f of x. And we realize then that when you do summation over all these pixel-wise contribution as defined by the integrated gradient, you eventually have the difference between f of x prime minus f of x. In other words, we are kind of breaking down the final prediction f of x according to f of x prime plus the summation over pixel-wise contribution. So in this case, the pixel-wise contribution is so nicely behaving that if you sum over all these contributions, you recover the original function output. Yeah, so it's like breaking down the final prediction into individual factors according to every pixel. So this is something called completeness axiom. Okay, so now the question is, what should be the baseline? Ideally, the baseline is an image without any information. And what comes to your mind, right? What comes to your mind? An image with all black pixels, for example, or gray image. Okay, so in fact, yeah, they also use a black image as their baseline. And if you compute the integrated gradient, you're computing a score map that looks like this. Actually, it's colored score map because you see you're multiplying this the original pixel values. So if x prime is node, then it's going to be minus original image. So you have the original image kind of visible for the parts where the attribution is greater. And and we kind of realize that compared to input gradient itself, integrated gradients are pointing better at the locations of the potentially important region in the image. Although we have all the, we know from the previous slide that we should not rely on human intuition for making comparison between different approaches for feature attribution. So although integrated gradient seems to give more sensible regions in the image compared to gradients, we cannot conclude that integrated gradients are giving better explanation. Okay, but with this caveat, still integrated gradients seems to work pretty well. But the biggest problem again is the fact that we need to set the baseline. And actually, since we set the baseline as black pixels, okay, if the original image has black pixels, like in this case, the camera is partially black, right? For those black regions, the attribution score will always be 0 or close to 0. Why is that? Because in the formulation of the pixel-wise contribution, we have this vector xi minus xi prime. And that value will be close to 0 if the original image has a close to 0 pixel value. And that sounds wrong, right? Because I mean, the black pixels here may contribute super well to the prediction of camera as well. So that's the biggest kind of drawback. So far, we looked into feature attribution for continuous inputs. Now, what about feature attribution for discrete inputs? Many of the concepts before, for example, gradients, are based on continuous interpretation of the space, of the input space. How can we take care of discrete input spaces? The challenge here, of course, is that gradient does not work anymore. And so we cannot rely on efficient backpropagation. But here, there are also like advantages of having discrete inputs as well. The good thing is that the input dimensions tends to be smaller. So there's usually less problem with efficiency. And also for discrete inputs, there's often a well-defined notion of no information. So for language models like BERT, which takes a sequence of tokens as an input, there's a predefined mask token that is precisely indicating no information. And you know, what BERT is trying to do is to impute the input. And there's a designated mask token, M, designed for indicating to the model what the model should be doing for that pixel, which is basically inpainting or imputing the token value. And also for text in general, it is actually quite often sensible to just erase the token and not fill in with any other value. The reason we had to fill in other value for images was because vision models are rather rigid. They take a fixed size input, okay? But for text, we have variable size input in many cases, and it doesn't make a big issue to just erase some of the tokens and make the length of the entire input a little bit smaller. Okay, so let's take a look at what kind of counterfactual question can we ask for discrete data. Let's think of spam reply classification task. So we have YouTube comments, and we wish to categorize each comment into spam versus no spam. So if you have Sai is a good guy, then you have class note, meaning that it's not a spam. And if you have for Christmas song, visit my channel, and that is actually a spam, okay? So now, after training a model, you are wondering why, for example, for Christmas song, visit my channel comment is predicted as a spam, okay? In this case, the tokens are, for example, each word in the sentence, right? The question is which feature is contributing the most to the decision that it is a spam. The way you can figure this out is by erasing certain features, certain tokens, and see what's the reaction of the model. On the left side, we show inputs and the original input and some of the counterfactuals. So you're erasing some of the tokens like this. And on the right side, you see spam likelihood. So for the original input, you have 99% likelihood. For the other cases where you raise some of the tokens, you sometimes see quite some drop in likelihood. So if you erase Christmas and channel, you see that the likelihood is now as low as 70%. So things like this is possible, right? And this is kind of close to what we have done in the continuous domain. So instead of making a small perturbation in the direction of EI, now we are entirely removing a feature I from X, okay, and call this Z. And we take a look at the reaction of the model and take, so contribution is now defined by the difference here. So how do we build an explanation with this, right? We can't just present this table, right? So the way we introduce an explanation, a concise explanation, is by fitting a linear model. Okay, what does that mean? So we have introduced a new column here indicating the presence and absence of each feature. So the original input will always be a sequence of ones, whereas if you have certain features missing, that's going to correspond to a binary sequence where 0 indicates the missing feature. And based on this, right, so we have this binarized input Z prime, right, ones and zeros, and the aim is to fit a linear model for the prediction of the stem likelihood. Okay, so the linear model looks like this: a beta note plus beta 1 Z prime 1 plus all the way up to beta D Z prime D. So for example, for the original input, the estimating function will look like beta 1 plus many dots and plus beta 7. And that's supposed to be close to 0.99. And if you remove one of these, then you're basically leaving out one of the coefficients, okay? And you have corresponding ground truth for that. So if you have a bunch of these, right, your equations look like this. So in the first row, you have summation over all betas. As you remove one of these, right, you have corresponding stem likelihoods. You can also try to think of this as system of equation, yeah. But usually for a system of equation, you need exactly the same number of equations as the number of parameters. But for this kind of situation, is probably not the best kind of model for training beta. But instead, yeah, also because we can have much more number of equations than the number of parameters, it's more suitable to consider doing linear regression, which is allowing for some errors, yeah, non-precise prediction of the stem likelihood, even for the training set. Okay. So we feed a linear model using L2 loss, right, as a usual linear regression. So we have different z's, which is indexed by n for the sample index. We just take the difference in the predicted likelihood and the true likelihood, and sum over all square distances. And we basically minimize this L2 loss for the optimization of beta. Cool. But now, since we are mostly interested in the vicinity of X, we're going to give more weight on the perturbations, which are not too different from the original sample. We do that by introducing some weight that's going to be put in front of every sample in the summation. And the way you can formulate this weight is by taking the Gaussian kernel, for example, RBF kernel. So you take the x of minus of the square distance of the binary vector. So if there are many omissions from the original input, then you're going to have lower score here, exponentially lower score. So you're predominantly considering more closer samples to the original. So that's the fidelity term for the linear regression. And you also put some L note regularization to induce sparsity. The reason why you do that is because humans are better at understanding sparse linear functions than dense linear functions, as we have introduced in the last lecture. And this formulation is called LIME, local interpretable model agnostic explanations. The reason why it's called model agnostic is because the model can just be any black box. Yeah, so you can basically pass through some of the perturbations of the input, and you just need to know the outputs of it. Yeah, so we have then input-output pairs from this model for the local vicinity of the original input, and then based on that, we just regress. We just find a linear, like sparse linear function that's approximating this this function. So yeah, that's line. And when you make a linearization like this, then you can also visualize this nicely using using this kind of visualization. So let's say it's a diabetes prediction. We can break down different features or rank different features according to their contribution to the prediction of diabetes. And the contribution is determined exactly by the beta values that you predict, that you estimate here. So the beta value for glucose was 0.12, and the beta value for diabetes, again, the beta value for age for diabetes is actually minus 0.08. So there's negative contribution for from the age side. And so on, right? So these are kind of breaking down the prediction of diabetes into different different factors. And yeah, this is possible because eventually you're breaking down the prediction into beta note plus, yeah, you know, like the prediction for the original input is beta note plus all the way up to beta 7, right? So beta node is referring to the case when none of the features are available, and then each of the betas here are kind of showing the contribution of each feature. So that's how you break down the prediction 0.72 into individual contribution of each feature. So that's LIME, which is quite simple if you know what's going on. Let's take a look at Shapley values. So let's start with another example. I could have used the same example, but I just wanted to give you another sample here. Gloomy, tense, yet profoundly interesting. Now the task is to tell if this sentence is a positive sentence or a negative sentence for describing a movie, right? So this is like Rotten Tomatoes review, and you want to figure out if the comment is kind of positive or review is positive or negative. So now the question is how much does inspiring here contribute to the positivity of the sentence? So now line was sort of input gradients for discrete inputs, yeah, because we were looking at the local vicinity of the perturbations. Now Shapley values is sort of an integrated gradients for discrete inputs. So let's see why that is the case, okay? So as a reminder, integrated gradients was looking at the line segment between x and x prime and was looking at the small changes to the direction EI at each point, okay? Which is great. And eventually the kind of formulation that you got was expectation over different alpha values across different uniform distribution. And you just take the difference between when you add delta EI or when you have just without this perturbation. We're going to show that Shapley values follow a similar formulation. Again, you're going from original input X, and at the end of the day, you want to remove um, all the features. And along the path, right, from X to no features at all, you're gonna figure out the contribution of I in each case. So what you're gonna do is along the path, you're gonna remove feature I for every member along the path. Okay, but to remove I, right, along the path, you need to choose a path where I is always present. So at the end of the path, for example, you're going to have a singleton of I. And if you remove I from there, then you're going to have an empty set. Okay, now, so along this path, you're wondering about the model's reaction to removing I. Okay, so you're going to take a look at the quantity of f of z minus f of z minus I, where z is an element along the path. And, in continuous space or in vector space in general, there's no nice notion of interpolation, okay? From one point to the other, there's a linear path. But this is a discrete space, and there's no such notion of linearly interpolating between x and a singleton I. So there can be different options here for moving from x to some faraway point. But among these options, Shapley values is taking the option of just considering every possible path. That means along the path here will not be a single path. It will be a multitude of paths that kind of constitutes any possible way of going from X to a singleton I. In other words, you're taking a look at any possible subset Z of the original input X with the constraint that the subset should contain I, because then you should be able to kind of exclude I. So the notation here is indicating that we're summing over all Z, where Z is a subset of X, of course, and Z actually contains I. So yeah, Shapley values phi of f and x at I is defined by the expectation over Z, where Z contains I, and Z is a subset of X. The difference between f of Z and f of Z minus I. Right, so this is Shapley values, and I need to explain a few more technical details about the expectation here. Here we are taking a two-stage approach for sampling from Z. Okay, so for example, we are computing these Shapley values based on samples. Yeah, samples of using Monte Carlo sampling. So we are sampling Z a few times and compute this f of Z minus f of Z minus 1 and just take an average of these. But when we do sampling here for the subset Z, we are not taking a uniform uniform sample, random sample from the set of all possible subsets. We do some kind of normalization of probabilities according to the size of the subset. So what we do is, first of all, we subset, we sample the subset size M from the length of feature X first. Okay. So we want to give kind of equal chance for each subset size to appear here. And then for a given size M, we are conditioning on the size M, right? Basically for sampling a subset of size M. We put uniform probability over all the subsets then. So the probabilities will take the form of x minus 1 choose m minus 1, because we know, first of all, that I should be in the subset. So the chance of the number of ways you can get such a subset is the number of ways you can choose m minus 1 elements, excluding I, from x minus 1 elements, which also excludes I. So if you write things down this way, each of the probability for the subset Z will take the form of 1 over x, which is basically the probability mass for the subset size M. Or in this case, we just choose we just write the size of Z basically. And each of the probability for Z will, given size Z, is given by x minus 1 choose Z minus 1 inverse, okay? And if you put everything together, you're going to have this kind of factorial formulation, Z minus 1 factorial times x minus Z factorial over x factorial. And then with this factor, you're basically taking the difference between f of z and f of z minus I. Okay, so that's exactly what Shapley values mean. And let's do a little bit of exercise on how this is computed in practice. So the original question was, how much does inspiring contribute to the positivity of the sentence? Then what we do is we consider a bunch of subsets of the original sentence. So the original is gloomy, tense, yet profoundly inspiring. You can leave out, maybe profoundly first, and then you get gloomy, tense, yet inspiring. You should still have inspiring here. And we can also remove gloomy on top of that, so we have tense, yet inspiring. And for each of these cases, we can measure the likelihood of positivity. And now, for each of these samples, we have a corresponding counterpart, which is when you remove inspiring as well. So now we have gloomy, tense, yet profoundly, full stop. Or gloomy, tense, yet, full stop. Or tense, yet. And then measure the positivity in each case. And then we take the difference between the positivity with the inspiring and positivity without inspiring. So 40% here, 50% here, and 50% point here. And, if you take the average of all these differences, then that's exactly going to be the Shapley value attribution for the feature I for this input X. Now, Shapley values also enjoy this nice completeness axiom as in integrated gradients. So if you sum over all attributions over all features I for the Shapley values, that correspond to the difference between f of x and f of note. So you're breaking down the change between full feature case and no feature case into individual features present in the input. So this is quite similar to the completeness axiom that we've seen for integrated gradients. When you sum over all attributions over all pixels, you get the difference between the baseline prediction and the current prediction. So this is it for the for lecture 6.